Today we discuss subspace. We already know what is vector space. This is a property in vector space. We already know. Now, the set of all ordered pairs of integers of Z is not a subspace over R with respect to addition and multiplication. How you can see it? Suppose you take two elements, one from suppose 3, 5. This is from Z. This is the order pair from Z, and half belongs to R. The vector space means we know where the Z is a vector space over capital R. Is it true or not? We have to see it. If we take 3, 5 belongs to Z and half comma belongs to R, we see that half into 3 equals to 3 by 2, 5 by 2, which is not belongs to Z. Which is not belongs to Z. That means this property, that is this property does not hold. So Z over R is not a subspace. Z over R is not a subspace. This is we already know there are 10 properties in a vector space. Vector space is a algebraic structure which has 10 properties. For all A belongs to F and alpha belongs to V, A alpha must belongs to V to become V is a vector space. Here Z is a vector space over R. It is true or not? We have to find it. Okay. So here we see that this property does not hold in Z. That is why Z over R is not a subspace. Now, there are variety type of subspace. At first, we have to know what is the definition of subspace. Here we see that V is a non-empty set and S is a subset of V. Here we see V is a non-empty set, S is a subset of V. Now, we have vector space, capital W, non-empty, subset of V. Now question is, when W is called a vector subspace of V over the field capital F. Actually, if W is a subspace, then W must itself a vector space. W must itself a vector space. Here we see that V is a non-empty set and S is a subset of V. V is a vector space over the field capital F. S is a subset of V. If S is itself a subspace, then we can say S is a subspace of V over the field capital F. Suppose Q over Q or R over Q over Q is a subspace of R over Q. Here you see that Q is a subset of capital R and Q both are the field. So Q over Q is a subspace of R over Q. But it is not mandatory that every subset of R over Q is a subspace of capital R over Q. But the primary condition is that the field must be same. If Q over Q is a subspace of R over Q, so the field must be same. That is, here we see that in both vector space, Q is the field, same field. If we consider V equals to R over Q, V equals to R over Q means R is a subspace over the field Q, and W equals to R over R. It is a then W is a subspace of V we have to check here that W is a subspace of V or not. Anyone can say? Anyone can say? W is a subspace of V, that is R over Q. Here we see that W is not a subspace of R over Q. Why? It is W is not a subspace of V, that is R over Q. Here you see that there is a difference in field. V is a vector space over Q and R is a vector space, that is W is a vector space over R. So field is different, that is why W is not a subspace of R. So we conclude some basic concept. Number one, you can write it. If field is same, then W may not be the subspace of V. If field is different, then W is not a subspace. If field is different, W is not a subspace. 0 and V is a trivial subspace. 0 and V is a trivial subspace. Number 4, W1 intersection W2 is a subspace. If we take W1 equals to x comma y comma 0, R3 and W2 A comma 0 comma C belongs to R3, then the element then W1 intersection W2, the element will be x1 0 comma 0, this type. You see that the non-empty set W1 has an element in this form, that is x comma y comma 0. If you take W2 is another subset which has element a comma 0 comma c. Here you see that third and second element of this tuple is 0. So intersection must be W1 intersection W2 contain the element in this type, and all element x1 comma 0 all element belongs to W1 intersection W2. If we take, suppose that means x1 comma 0 belongs to W1, x1 0 belongs to W2. This type of element both present in W1 intersection W2. That is why W1 intersection W2 is a subspace. Similarly, if we take number 5, W1 union W2 is not a subspace in general. It is possible only W1 contain W2 or W2 contain W1. In general, W1 union W2 is not a subspace. It is possible only when if W1 contain W2 or W2 contain W1. Let's take an example. If we take W1 equals to 1 to 0 belongs to suppose x1 x2 comma 0 and W2 belong to x1 0 x3 let we take W1 is a non-empty set which contain the element in this form x1 comma x2 comma 0 and W2 be the another non-empty set which contain y1 comma 0 comma y2 in this form. If we take W1 union W2, the element belongs to W1 union W2 will be A comma B comma C in this form. If we take union, so the element will be A comma B comma C. But we see that A comma B comma C does not belongs to W1, A comma B comma C does not belongs to W2. So W1 union W2 is not a subspace If we take another example, W1 120 120 belongs to W1 and 25205 belongs to W2. That is alpha, that is beta. If we take alpha plus beta equals to 3, 2, 5, which does not belongs to W1 union W2. If we take W1 equals to 120, W2 equals to 205, that is, which does not belongs to W1 union W2. Now, how to check condition to become subspace. What is the basic condition? Number one, alpha belongs to W, beta belongs to W. If it implies alpha plus beta belongs to W. Number two, C belongs to F, alpha belongs to W. If it implies C alpha belongs to W, then W is a subspace over F. This is the two basic condition. That means this is a additive property and this is a homogeneous property. There are two basic conditions to a non-empty set become a subspace. That is, if we take two elements from W and the closure property, that is alpha plus beta also belongs to W. If we take C belongs to capital F, that is field of scalar, and alpha belongs to W, then C alpha must belong to W. If W satisfies two conditions, then W is a subspace over A. And the combined these two condition, combined condition is A comma B belongs to F and alpha comma beta belongs to W. Then if A alpha plus B beta belongs to W, then W is a subspace over F. If we take two scalar from F and two vector from capital W, and if we take a linear combination of alpha and beta, that is A alpha and B beta, if A alpha and B beta also belongs to capital W, then W is a subspace over F. This is the basic criteria to get a subspace. Okay. So one is additive property and another is homogeneous property. These are the two conditions. So if you asked how to show a non-empty set is a subspace, at first you have to take two elements from the non-empty set and get a linear combination of these two vectors. If we show this linear combination also belongs to capital W, then you can say capital W is a subspace over the field capital F. This is the basic condition to get a non-empty set be a subspace. Now we take some example. Now we take some example, that is xy is an element in R2, and the property is we have to show W is a subspace. We have to show is a subspace of so at first what we have to do? At first we have to take two vector from capital W. Let alpha be the two vector. Let alpha x1 y1 and beta equals to x2 comma y2 belongs to capital W. Okay. If alpha belongs to capital W, then alpha must satisfy the relation, that is 3x1 plus 4y1 equals to 0, and beta also belongs to capital W, so beta must satisfy the relation, that is 3x2 plus 4y2 equals to 0. Now we have to prove capital W is a subspace. So we already know to prove W is a subspace, we have to take a linear combination of two vector alpha and beta. Let's suppose A alpha and B beta be the linear combination, that is A into x1 comma y1 and B into x2 comma y2, that is A x1 plus B x2 comma A y1 plus B y2. If we see that this A alpha plus B beta is a vector, is a linear combination of alpha beta. If we see that A alpha plus B beta also belongs to capital W, then W is a subspace, because this is the criteria to get a subspace. Now, but if A alpha plus B beta belongs to capital W, then this vector must satisfy this relation. If this vector belongs to capital W, then this vector must satisfy the relation. Now let us look the relation 3 into Ax1 plus Bx2 plus 4 into Ay1 plus By2, that is A into 3x1 plus 4y1 plus B into 3x2 plus 4y2 equals to A into 0 plus B into 0 is 0. That means this vector also satisfies the relation, and from if it satisfies the relation, then it implies that A alpha plus B beta also belongs to capital W. Now, so here at first we take two vectors from capital W and get a linear combination of these two vectors. If this vector satisfies the relation in capital W, then you can say that this vector also belongs to capital W, which implies that capital W is a subspace. Okay. So, to get a subspace, we have to we choose two vectors from that non-empty set and get a linear combination of these two vectors. Then if you see that this linear combination of these two vectors also belongs to the same set, then the non-empty set is a subspace. Take another example. First example, we see that the non-empty set capital W is a subspace. Here we prove that capital W is not a subspace. Capital W is not a subspace. Here we see that capital W is a non-empty set of matrix over capital R, and matrix is the form 2 cross 2. If we take, let's suppose, if we take A1 equals to 1 0 0 0, you take date 1 equals to 0. If you take A2 equals to 0 0 0 1, then A2 equals to 0. That means both A1 and A2 belongs to capital W. Both maintain the same order of the matrix and both maintain the condition in capital W. Now, if we see that A1 plus A2, what happens? What happens? A1 plus A2 equals to 1 0 0 1. Let's take it as B. B equals to A1 plus A2. But you see that mod B not equal to 0. Mod B not equal to 0. Because this is a unit matrix of order 2. And mod B not equal to 0. Now here, what we see? Here also we take two elements from capital W. One element, that is A1, whose date value equals to 0. Another element we take whose date value also 0. If we take addition of these two vectors, we get another vector, another matrix B of the same order, that is 1 0 0 1, which is a unit matrix whose date value is not equal to 0. That means it does not satisfy the basic condition of subspace. We know if alpha comma beta belongs to W, then alpha plus beta also belongs to W. When W is a subspace. If alpha beta belongs to W, then alpha plus beta also belongs to W, if W is a subspace. But here we see that if we take two elements from capital W, that is A1 and A2, and both satisfy the basic condition of capital W, that is the value of the matrix is 0. But here we see that sum of the two matrix is also of the same order, but the value of the matrix is not equal to 0. That means this, the basic condition, that is this condition, if alpha beta belongs to capital W, which implies alpha plus beta belongs to W, then W is when W is a subspace. And this condition does not satisfy, and that is why we say that capital W is not a subspace. Capital W is not a subspace. Now another example. This is a non-empty set of function. This is a non-empty set of function. The capital W, what is capital W? Capital W is a non-empty set of real polynomial. Now we have to show whether capital W is a vector space or not. From the previous example, at first what we have to take? We have to take two real functions from capital W. Let's suppose W1x belongs to capital W, K1x. Both belongs to capital W. K1x and K2x both belongs to W. If K1x and K2x both belongs to capital W, so both function must satisfy the relation. That is 0 to 1 K1x dx equals to 0 and 0 to 1 K2x equals to 0. Now we have to show the linear combination of these two functions. We have to show the linear combination of this function, that is A K1x and B K2x also belongs to capital W. If capital W is a subspace, then the linear combination of K1x and K2x also belongs to capital W. Now, but if these linear combination also belongs to capital W, it is possible only when if this element satisfies this relation. If this element satisfies this relation which is in capital W. Now, let us see 0 to 1 A K1x plus B K2x dx. So on A 0 to 1 K1x dx plus B K2x 0 to 1 dx. So on A into 0 plus B into 0, so on 0, which implies A K1x plus B K2x belongs to capital W, and which implies capital W is a subspace of capital V. Here I give three examples. One from real matrices, another from real polynomial, and in all cases what we do, we take two elements from that particular non-empty set and take a linear combination of these two elements. If we see that linear combination also belongs to the non-empty set, then we conclude that that non-empty set is a subspace. We see that in three cases, same procedure. Now, if we check, this is one type of question in there Here we see that W is a non-empty set. In 4 cases, we see that 4 different conditions. Now, we have to check which are subspace and which of them are not subspace. In first case, let's suppose first case. If we take, how to check? If we take 2 elements, let's suppose 1, 0 belongs to R2. 1, 0, this satisfies the equation. And if we take 0, 1 also belongs to R2. But you take the sum of 2, 0, 1 plus 1, 0, that is 1, 1. If we take 2 elements from R2, 1, 0, 0, 1, both satisfy the condition xy equals to 0. But if we take the sum of 2 elements, which become 1, 1, and product of these two conditions, and this element, this order pair cannot satisfy the equation. That is why this is not a subspace. When you can say subspace, if you take 2 elements from that particular non-empty set, and if these 2 elements belongs to capital W, and the linear combination of these 2 elements also belongs to capital W, then capital W is a subspace. Where you see that 2 elements, that is 1, 0 and 0, 1, both satisfy the relation xy equals to 0. But sum of these 2 elements, 1, 0 is 1, 1, which does not satisfy the relation. That is why capital W is not a subspace. Now, we take another example, that is this. Is it subspace or not? Anyone can say? Subspace. Why? Let's take an example. Suppose 1, 1. This satisfies the relation, and 1, 1 belongs to capital W. If you take 1, -1, this also belongs to capital W. But if you take the sum of these 2 elements, 1 plus 1 plus 1, -1, that is 2, 0. Is it satisfies the relation? 2, 0 satisfies the relation or not? So, if this does not satisfy the relation, then which is the conclusion? Conclusion behind is that capital W is not a subspace, because sum of 2 elements does not belongs to capital W. That is why W is not a subspace. Now, for capital C, for C, is it a subspace or not? Is it if x square plus y square equals to 0? It is possible only when x, y both is 0. You already know it. That means it is always subspace. It is always subspace. X square plus y square equals to 0 means we conclude x equals to y equals to 0. That is why capital W is always subspace. Okay. So to check a non-empty set is a subspace or not, at first you have to take real example and give a linear combination of these two elements and check whether the linear combination belong to that particular set or not. If it also belongs to that particular subset, then the subset is called a subspace. Okay. Any question regarding subspace? Basic criteria or basic concept of subspace is the subspace is nothing but a subset of the vector space capital V, and subspace, and that subset is also a subspace, is also a vector space, itself a vector space at first. If you see V is a vector space and S is a subset of V, all subset is not a subspace, but if S itself is a subspace, then S is a subspace of capital V. And subspace maintain two criteria, additive and homogeneous criteria, and combine these criteria you get if you take alpha comma beta belongs to V and A comma B belongs to field of scalar, that is F, and get a linear combination of alpha and beta, you get A alpha plus B beta. If you show that A alpha plus B beta also belongs to capital W, then capital W is a subspace. Anything else?